Okay, no faces. Okay, let's, I guess, start with picking the problem again. We are up to what? Were we at 15 last time? I guess
15? I think we 25.
25.
20 or 25. I think it was the last.
I may have skipped one folder.
I think that's the last.
I think this is the last one, and I found this one is still closed, so I think we skipped one level.
Mm-hmm. Well, that's good for us.
Yeah. Okay. So problem 64. Okay, lots of text. Let's see. Odd period square roots. There's two sides.
Long description.
What?
Trying to understand this, for example, let's consider.
Why is he doing this?
Okay, -4.
Okay. What am I missing?
This passage is not clear for me, like in the from here to here.
Well, I think he's trying to transform the 23 into this form, into the top form. So he's trying to, okay, well, he pulls out 4, which I'm guessing because that's the first part, the first digit in the result. And then he's trying to move the rest down here and keeping this all the while as simple as possible.
Yeah, but from that to that is not clear.
Oh, you mean, oh, the transformation is not clear. Okay. So, well, so 1 divided by 1. So this is, I think, so this part is clear, right?
Yeah.
Okay. And then the question is, how do you get from this to that? So let's see. That's a good question.
I'm trying to do the reverse.
So
like from that to the other one.
We could just see if it is actually true. If we want, could just say, okay, what is square root of 23 1 plus 1 over minus 4 So for what it's worth, it's true.
It's true, but this is floating point, Python floating point.
Yeah, I mean it's probably true. I'm saying. I mean, and that doesn't mean I know the transformation, but it. I mean, who knows who wrote this? We could have guessed maybe that he's doing something wrong, but probably not. But the fraction isn't even correct, is it?
Fraction?
I mean, this is this supposed to be the successive digits?
Mm-hmm.
Because This is not what Python says.
No, it's that thing is those successor will be repeated.
Okay, but this is not the same as the decimal digits.
Ah no, it's not the decimal digit.
Okay.
They're like A is A-N.
Okay, so this is just some other form
Yeah.
to write it. Okay. I don't know why does he pick 4 in particular?
Because like square root of 23 is 4, comma, decimal number.
Okay, so if that's why he does it, then
yeah, here I want to understand why this.
Okay, let's try that.
Yeah, this is, and then I found it here.
Okay. So, but this is still the thing, 1 over this, and then okay, so square root no. So you pulled the 4. No.
Plus 4. This is 1 over. If I do multiplication of plus 4 in the bottom and also in the top, plus 4. I think I found it.
Okay.
Yeah. So yeah. So if we want to transform this to check if it's equal to this, we multiply the this fraction in by square root of 23 plus 4, like in the top and in the bottom. Then it will be like 23 minus 16. We have something like that. A minus b multiplied by a plus b equal a square minus b square. So then we will have like 23 minus 16 over 23 plus 4. And then we will have this.
Yeah, then
we add the
Now the final step here is then pulling the 1 out of here. So this is, if you
do plus 3
minus 3 plus 7, and then you can pull out the plus 7. Okay. Fair enough. Okay, and so the idea being to always pull out the largest number. Okay, so let's just look at the second case. So we're starting with the, well, he flips it around again. Okay, again with the 1 over 1 over this thing. He flips it around. Right?
Yes.
Same thing here.
Same, yeah.
But again, he picks his digit to pull out based on what exactly?
He pulled the 1 because he has in the previous one.
Okay, but why didn't he do wait, so he's looking for, what is he looking for? So why did he I mean, he could have picked, I don't know, 14. Yeah, he could have picked, instead of -7, he could have said -14, and then he would have had -9 and 2 here. Why not that? Because he wants to have minimal, the minimal thing. Obviously not, because here he has something else, right? Why? What is this about? It can be seen that the sequence is repeating for conciseness. Okay, what is the pattern? I don't know. Again, I'm not quite sure. If you say that he picked out the 4 in the first case in A0 because of square root 23 is first 4, then presumably he's doing the 1 here for some similar reason. So the first digit of this is 1, is that what we're saying?
Yeah, I'm not sure, because like you can like do -10 and then have 17 as the...
Yeah, you can pick anything you want.
I think you want to keep the 7 as a base always.
The 7?
Because he got it.
No.
No. Right.
The first 10 continued fraction representations. Continued fraction representations of irrational square roots are interesting. So what is he, 23? Okay, and he says that because, okay, so there's a loop here, because this is this, this is a period of 4, I guess.
Yeah.
Mm-hmm.
I think we want always to get the smallest number, like the 1 and 3, 1 and 8. Always we want the smallest one. We can derive any number, but we want always the smallest.
Okay, so how does this work in this case? He's starting at 7. Okay, he's starting here. So how does this work?
Yeah, he multiplied by the square root of 23 plus 3, like in both,
right.
And then he got 14 in the bottom because 23 minus 9, and then yeah,
and then you cross out this. Okay, but then you have square root 23 plus 3. So why don't you go plus 1? Or rather, I don't know, why does it go to -3? So so you're looking at square root of 23 plus 3 over 2, and from there he decides that he wants to I guess subtract 6, right? Oh wait, no.
No, because you can subtract 7 and 7 from both bottom and top, from like the 7 that is attached to square root of 23. Yeah.
This is gone. We're looking at square root of 23 plus 3 over 2 because cancel, or are we not? I think we are. And so then why the 3 here? So 2 times 3 is 6 to get in here, so this is 23 minus 3 plus 6.
Yeah, in that case he hadn't to add anything. It's by its so it's like square root of 23 plus 3 over 2. Yeah. And then he did minus 3. Yeah. 1 minus.
Okay, maybe this is the key. So the main thing is that you want to have a portion here and 1 as the top part of the on the numerator. So you have to have 1 on the numerator. And how do you get 1 to be in the numerator? Okay, so you do this switcheroo. Is it really, maybe I'm on the wrong way, because even here, you can you can pick any number here and still have 1 in this part of the equation, right?
Yes.
So this can't be it. Okay, so assuming that we call this the rest in the case of A0, then we pick this based on the square root of this being 4. Then in this case we are picking the number we pull out of here based on the square root of this whole thing. No, just based on the lower value of this. So floor of this, right? So that would be 1. And in this case, we are picking, so we have, what do we have? So here we're pulling 1 out, and here we're 23 minus 3, 23 minus 3 over 2, and here we will presumably be picking 2 out. And, oops, and 3 plus. No, plus. No, I think I understood. So here we have 23 plus 4 over 7. Okay, and here we have 23 plus 3 over 2. So we should be, yeah, pulling 3 out. Okay, fine. Yeah. Okay, so that seems reasonable. The question is, can we do this without square root? Do we even want to? Also, we should probably not be using floating point. We should probably be using, I don't know, some symbolic representation, because we want to be able to compare, right? We want to be able to see whether or not we've seen this number before.
Yeah, we want to,
Specifically this thing, yeah.
Period.
Want to be able to see that A1 is the same as A5. So we could just, I don't know, is this form seems, okay, so we always have this form. We always have a leading digit, numerator, and a denominator composed of a square root, which is our original square root, I guess, and then the, I guess, whatever this we want to call this. So we could have tuples of those, and then we can know whether or not we saw it before. Okay, but onward, what do we have as even the problem? So exactly 4 continued fractions have an odd period, the periodicity. How many continued fractions have an odd period? See that the sequence
odd period is for number 13.
Pardon?
The odd period is for the square root of 13 as a period of 5.
Correct.
So we want to look through all the number from 1 to 10,000, I guess, and collect the number of odd periods.
Probably, yeah. I don't suppose we can say anything from the outset what the period would be. You might be able to recognize a pattern or something. Is there something like, okay, so we have the 2, we have the 5, we have the 10 and 13. Two, 4, 3, step.
Exactly for continued fraction.
Okay, then I guess we'll assume that we can't. Yeah, this doesn't sound like computationally very challenging. Okay, let's see. So I'm not going to write down the problem. I'm just going to insert cell above, mark down. And people can click. Okay, so we have a function def get period, or what is it called? Do you have a name for this? I guess continued fraction representation. CF or get. I don't know. So we'll get the CFR for, I suppose, this is big N, right? Yes, so we'll just do big N. And the first thing I guess we'll do is square root of N, because we'll be calculating that a lot. We'll be using that a lot. And the next thing is, I guess, do we have a name for this kind of thing here? Sequence. I guess they'll call this A. We'll call this, so this will be A0 and A1 and so forth. So let's just generate, what is it? Wait a minute, I know what to do. I'm wondering if I should use attrs. Do we even have attrs? Import attrs. I don't have it. Let me just check. Nope. Let's see. Mux and This is just because I don't want to deal with name tuple anymore. Okay, we'll call this no, still don't go. I think it's called header. Okay, at Python atters. So there's a frozen thing here, isn't there? Frozen. Oops. Wasn't there? Okay, Python atters frozen. Go. Frozen. Okay, so I didn't remember that correctly. Frozen true. And stir these now. Okay. Attrib, so this is the kind of thing. Fancy pants. The class A. Okay, so we'll call these things, let's see, A, B, C, D, E, A, B, C, D. We'll call it, so since we always have the square root 23, I will just not do this. I will call this the digit and the numerator, oh yeah, let's call it, I don't know, leading as an L.
Yeah. I think if the number is like for example 9 has n as square root, we can just ignore it.
Pardon?
If for example for 4 or 9, like numbers that their square root is an integer, we ignore them.
Ah yes. Okay, so yes. Do you want to trust the floating point stuff here? Or do you
I think we'll use decimal maybe.
Okay.
Well, thinking if there is like possibility to how to get that one.
I don't know. Okay, well, let me just try something first. So I think it converts that.
I'm thinking about like where we don't have to calculate the fractions like
yeah. No, it's like okay. I don't know, we could round it and multiply it. I mean, it wouldn't be wrong. Yeah. I'll just do that for now. If you find something better, then by all means. If round square root n, I don't know. Where is it? 1? So what is 9? So 9 is period 0. Okay. So n is not that simple, is it?
Yeah. It should be solved recursively.
Should be good. I don't think so.
No.
Maybe. I don't know. So prev avals is a set which we start off with a0. So while
I think a0 not included. No.
Why not?
Because the period is always what's after a0.
Yeah. Okay.
Yeah. Here in the example, for example, for square root of 2, we have 1 and then period of many 2's. And then
Okay, so well, then we're capturing our CFR in any case, and that will start off with L. And we're not putting this here, and we are saying while, and we're going to keep track of AN. So this is our nth A value. So while AN not in prev A vals, we want to generate the next AN. And at the end, we return CFR. Actually,
not in.
No?
And the prev is set. Shouldn't be like a list, because we want to keep it its a period.
But we are only, yeah, that's what the CFR is. So the CFR is this, and the prev avals is a list of these things. Or a set. It's a set. And so I guess I start off with not putting it in there, and I then put CFR append L, an.L. Yeah. So now all we need to do is do an equals big A, and well, okay, so what do? We do, the first thing is we calculate this.
Yeah, but I think you should know how to get it from the first A0.
I don't know, I think the so this step seems to be okay. I think this is okay. Let's see.
The first thing is the multiplication, like
Okay. I mean,
I think that this can be solved by, we take always the decimal part and we do the inverse. We do the then we do when we do the inverse, for example, here we took this, we did the inverse, and then if we calculate that, it will be one, like comma, a number. And then we take that number and we do its inverse, it will be 3 comma number. Then that number.
Okay, so we just calculate this first. Okay, very good. Okay, so L is very simply an n divided by, well, no, an dot L plus an divided by, I guess, square root of n and minus an dot d. I shouldn't strictly call this d, it's probably confusing because there's only one part of the thing, right? Yeah, so this is that. And
what is L and N?
So, yeah, okay. So if we take this case, I don't know if this is possible to format. No. So if we take this as plus square root 1 over square root of 23 minus 4, then we have L plus n over, this is kind of like the square root n minus d. I don't know, if you have better names, then we can pick something else.
N shouldn't be
the numerator.
Okay.
So in this case it will be 1. So
I think we don't have to see what is the value of n.
We don't?
Yeah, because after doing this, I
think we do. But you think it's always 1?
No, I don't think it's always 1, but we don't have to check that value.
Okay.
Calculate the next.
Is it always implicit?
I mean, we can calculate always this whole value, for example. So after we did this 4 plus minus that, we calculate that number.
Yeah.
And then we do the reverse.
The inverse.
The inverse, yeah.
I don't think we do the, I'm not sure. So I know, okay, so.
And if we do the inverse, it will be 1, like we calculate the inverse of that number, it will be equal 1, comma, a decimal number. And then we take that decimal number, we do an inverse. It will be 3, comma, another decimal number. And if we do the inverse, it will be again 1, and then, you know what?
Oh, no, I'm not following.
You can explain. Can be Maybe, I'm not sure if this is correct or not.
Second. Okay.
So if we do a square root of 23, it's 4 comma a number.
Yes.
Like this or this. If we can take that number and we do the inverse, it will be 1 comma another. And then we take that number and do the inverse again, like 1. It will be 3. And we only want this 1, 3, and then we do inverse of that.
Okay, so you're happy to do the whole. You want to do this in decimal, I guess. Okay, maybe.
Think this will work.
Well, it depends, because you say you have this number, but this number is square root 23. So there's precision lost in some cases. But you're saying it's probably enough. Okay.
So that's why I said we don't have to calculate those number exactly. For example, the 7.
Okay, but how do we know that we've reached the?
We get in those 1, 3, and then we store in them, and if we see them again.
Okay.
And maybe we can.
Maybe I hope I wouldn't. Okay, I wouldn't say it's impossible. Okay, let's try that. So we're going to do fraction. So let's see. Okay, so we're going to do math square root, or maybe we start off with fraction of n, and maybe let's see what it does with this 23. So let's see what it does if I do math dots. Well, I think math dot square root. So Python fractions square root precision. Yeah, we'll have to increase the precision. That's for sure. I'm just power to the power over half. Maybe that's how it works. Okay. Half is fractions. Fraction.
I think it is not that big matter because we are getting the decimal numbers and we are only like gathering the number that are the integer part. So I don't know if we can do the reverse. It will change from like 4 to 3. For that reason, it should be like very bad precision. I mean, even it has bad precision, it will do not affect much our calculation. But yeah, maybe if there is very long sequence of fraction, in that case, we'll have a problem.
But in any case, the type of this thing is type square root. So he's already losing. You're not keeping it as a fraction. This already turns it into a float. Let's see. Power.
We can do power like power half. It will be.
That's what I did. I did a half as a fraction and did power. and it produces a float. So, but maybe there's
it shouldn't always produce float.
Maybe that's how half is defined. That's why I'm trying to see if there's a Python fractions power, I guess. Right. Maybe decimal. I mean, we're talking about precision anyway. Okay, yeah, decimal is probably better. Decimal. Okay. Power. Okay, so this has power. So let's do decimals. Decimal. And I guess 0.5 and decimal this to the power of that produces a decimal of certain precision. We can say decimal set context decimal. How does this work? Context.
Maybe exclamation.
I think I'm almost precision. Prec. Get context. Prec. Okay, well, let's just do this. No. I don't know. Let's just do 100 for now. Yeah. Fine. Plenty. Does that look like 20? Okay.
Shouldn't be 22?
Yeah, maybe. Okay, it does what it's supposed to do. Oh no, it shouldn't be, because this is also a digit. So it is 1 and then 19 more and then the period. So it's okay. Okay, let's see. So the idea was to take our an, and we start off with square root of n, and we do an. Well, unfortunately we don't have the convenient denominator here, but probably we can do round. I can just do int probably. Int. Let's do print int of an. See what that does. Fair enough. Okay, so we do
minus the an.
So our digit is int an, and we do the next. I don't know. Let's an.
Yeah. an receive 1 minus 1 over maybe the inverse to get the next an, and the inverse of that 1 over. If we do that, is it 1?
Well, first of all, let's hope it's a decimal.
Oh, seems good. And then the 25 will be 3. Yeah.
And we do this, I don't know, let's just do it for a bit. For I in Orange, I can type 10, I don't know. Let's do this. So D is that, AN is that, and we should get, let's see, D.
Store DN.
Yeah, let's, so CFR is a list, and we start off by doing CFR append D, and let's just print CFR. Looks about correct, yeah. Okay, so and now we need to make sure that this, the question here is how much is our precision messing with us. So this has to be the same as that, right?
Yeah. Not.
So let's do the desperate thing, and
we have to check more. No, but maybe if I think if the imprecision gets closer to the point, it's
okay.
At some point it will change.
Okay, so let's do. Okay. Okay, let's do first of all the max that we can do without messing up our formatting.
Yes.
How about that?
Exactly.
I think I could have done one or two more digits. Okay, so where do we end up? We end up. I should have started from the other end. Okay, so here this seems to be the limit. Okay, so
this is 45, 43 or 44 precision.
So what do? We store something like, okay, so let's store the representation with, I don't know, I think you can get rounding thing of this, can't you? Let's see. Decimal, round. No? Okay.
End of this. What do you want to do?
Well, I want to, so we need to have something to compare against, right? So we have our AN here, and we want to see, have we seen this AN before? And so the simplest way that I think we can do this is having some set of those values in the rounded form, which, yeah.
No, that's, I was thinking about storing this, like, but it would be very complicated. So, like, it will be very complicated, like list of three, at first 2 elements, we see if that pattern is repeating, list of then 3, then 4.
Oh, you want to look at the pattern?
Yeah.
Well,
it's not
guaranteed.
It's not. It would be another Euler problem.
Yeah.
Yeah. That, so yeah, checking if the number is in the set would be much better solution.
Yeah. Only we have to figure out how to do it. So the decimal.
What is the probability if we take like even 10 number after the point, and if it wouldn't like match the same number that we are looking for?
I don't know how to, if this is a question of probability. I think the error. So we start off with some error here, right? And I think we're compounding the error.
Yeah.
So we can look at, for example, we could do something like if if d equals 1, we can see if we can compare the values, and we can see how messed up is becoming. Okay, so let's do if d equals 1.
An equal 1.
Well, an is never equal 1. So d equals 1, I guess, and an less than 4, let's say. Oops. And an. Okay. So here we can maybe see how the precision is behaving. So here we start off with that as the common digit, and then we lose 3 digits, and then we lose 3 more digits, and then we lose 3 more digits.
Can we do more like a range of 40? Yeah, the only problem is if the... Oh.
Yeah. But, okay. Let me do stir an. How much does he do there? I don't know, is there, I don't know, there's already this. Okay, so let's just do here, dip up to, I don't know, 50. Okay, so here we have some limit on this stuff, and let's crank up to, I don't know. So we're delaying the inevitable, but we can delay. I don't know, the question would be
the number of periods if it's getting higher, so we lose on precision. And then
yeah.
But here if we from the third one we are already seeing there is the same number.
Yes, so that would be the question, if we can somehow detect that we're getting too crazy. The question would be, what is the
how many continued fraction?
Yeah.
And have anode period.
Yeah, so is there some number, I don't know, 5,100 something, that has a period that is long enough that our precision is not enough because it has so many periods? And we could do some, I don't know, it seems a bit hacky, but we could in theory do something like, okay, we start off with precision, let's say 100, and as soon as we see our period of CFR has gone too high, we do it again, but this time with more precision.
Yeah. Can we do a number big instead of 23?
Okay.
Like 500.
But this time I need to figure out how. Okay, so this rule doesn't apply anymore, right? What am I doing? Why is this so... because we're at this here now.
Well, it seems like have 2 periods of 11 and 22.
Okay, so we need to find one that is not so nicely periodic. I don't know. We are one where
in the bottom.
Yeah. I don't know. I think
511, 522, 5111.
Do you have a favorite number?
47.
47.
Yeah.
If I could only type. Yeah.
Oh, 136.
The question is that because it's breaking, or is that because it's okay, so let's see what is the first thing. So we have 22, 14, 14, 22, 22, 14. So we have 136 somewhere else again. So we have, maybe that is the period. Okay.
And then there is 108,000.
Let's see, wait a minute. 136. Dude, I wanted to have
another line.
my mistake. I need to be able to. Okay. We're already pretty at the limit. This doesn't look equal to me.
There is 1,000. If you go to the top, there is 1,000. Yeah.
Okay. So this is
what is the precision? 100.
100. Yes. So 136. So we can try this.
Oh, looks the same.
Yeah.
It was fast.
Well, I don't know. Is it really that fast? So 100 milliseconds, and we have to do 10,000 values. $10,000 divided by 10, we'll be waiting 1,000 seconds divided by 60. We'll be waiting 16 minutes if we do this precision.
But for a range of 100, what if we have a repeated loop that
right, it'll be shorter.
More.
Yeah, it'll be shorter. Okay, let's try it. Okay, again we have to, I guess. Okay, so we'll have the prev.
Maybe we can break early if we find the pattern. We don't have to wait for this 100.
Yeah, sure. Yeah, I'm sure. I know. So we're going to have the A-vals in a set, and the A-vals are going to be A-vals add stir an limited to some kind of precision. So let's do, I don't know, 100. And we'll see if, so while an not in A-vals, we continue. And let's see, we are looking for the CFR. So CFR is the length of this minus 1, I believe. Print as CFR. Actually, this is the thing we can probably reuse, right? No, we don't need that. Right? Okay, so let's do Interesting. Let's see. Wrong. So I don't compare AN, I need to compare this thing. So the first, okay, also the first thing we do is put this in here. And the second thing we do is compare this. Okay. So let's just do for I in Orange, what is it up to? 14, 13, print, boop, I, comma, this, I, and let's
break.
What?
One eyes.
Let's, I guess, comment out this. So let's see, 2, 1, 13, 5. Seems okay. Seems okay. So yeah, but it's still slow. So how much does this help? So this forks us break or interrupt kernel. So this is already breaking at square root 2. Interesting.
Because there is.
Oh, right, because of this. Okay, so I have to do, I guess. So I think this should be part of the prec. Let's start with 100, and let's say, what do we call? CMP prec is just prec over 2, and we set the precision here, and we do the CMP prec, and we make sure that it's integer, and we start off with prec. Yeah, sure, let's start off with prec 100. So this is fine. How far can we go with this? So this is the failure case, right? I guess. If we have, is it still calculating? It should.
No, it's correct.
But it got this wrong, right?
It's correct.
Let me. Okay, so let's CFR. Let's, instead of doing this here, let's do. La di da di da. What am I missing?
I think closing parentheses after the last line.
Oh, yeah. I didn't even need this. Int object. Oh, right. Sure. Whatever. Okay, let's just put n in here. Awesome. So it looks the same as before. That's interesting. So I can go all the way down with precision to, oh, well. Okay, so
yeah, wrong.
Is it still running? No. But okay, so how do we detect that it's wrong? Do we not detect that it's wrong? I think we need to detect if it's wrong.
We do two loops, one with big precision and one with smaller precision, and we compare them. Every return the same thing, it's correct. But too big enough. Get to it.
Okay, you know what? No. It's unfortunate. I will just count the loops. I will just count the loops. So if I greater than something related to precision, so let's do, I guess, let's do CMP prec for all I care. Then we do return and we try again with prec times 2.
But the stopping condition should be changed. We should do 4, no?
What?
Shouldn't be the stop condition changed or no?
What stop condition? No. We just forget about all of this.
Okay.
Right? I wonder how far he went. Let's just track how many often we print prec. How far did he go? He went down quite a bit. Yeah. It's probably conservative. I don't know, it's a parameter, so this is like I don't know. Anyway, we'll be adjusting that one maybe. Let's see. So we start off there, we do this, and now we can actually look at the whole thing. So let's do 4i in 10 frickin' 1,000, and we count odds. So norm odd CFR 0. So this is CFR len if CFR len mod 2 is 1, then 9 plus equals 1. So what did he say? He said less than equal to, so 0, 1. And so I'm just going to, if I mod 100 print, then let's just do num mod CFR, just so we have some kind of progress indicator. Num mod CFR. Oh, that's not too bad. Interrupt kernel. So this will give us 10 lines. Oh, well. Zu früh gefreut? It's still not. Okay. Could be better. So we're looking for 100 of these, right? Yeah. Okay. What did I do?
Division by 0.
Okay. Interesting. AN minus D. AN minus D. AN minus
previous one was. Oh, I think we lost precision at some point.
Yeah.
So the int will be equal to the digit.
Yeah. Okay. So I guess this means that.
What if it's the first round?
What if it's the first round?
I mean, we had this division by 0 at the first step. But we can just do it.
So let's just note that we had 8, 8, 2, and if we multiply by 3, let's see if we get there at the same time, the same thing.
It's going faster.
Can't possibly. We should also print I. It's a better progress indicator, I think. So we get a different thing. We didn't even get as far. We got hit earlier. That's interesting. We can also, I guess, start off with a higher precision. Maybe it's in the first loop that the issue is there. I don't know. Let's start off. We got further.
Almost done.
Well, assuming it works. Otherwise, I mean, if it doesn't work, I'm going to bump up these things further and just let it run, and then I think we can see if we can take a look at this solution again. So let's try. That one. Oh, good. So I go, okay, let's do, I don't know. First of all, let's do, I don't know, 50. Let's do 50, and let's also stop doing this quite so much. And let's, I don't know, 10. This is much faster than I assumed. Why is this? Maybe we're going down a false road, losing precision, and it was aborting because it's churning on a thing that is hopeless anyway. And if we get to the correct result faster if we have the precision sooner. Maybe not. I don't know. The other thing is this this thing. So we could abort earlier, or we could abort at a more appropriate time. I don't know what appropriate would be, but this is still faster than I would have thought. I wonder what the longest fraction is that we have. So quite a few false positives. Sanity check. Yeah. I don't know. Still fast enough. All right. So in principle, this is the same, right? Well, apart from the fact that we don't have to do recursion because we know that the result will be correct. We don't have to do this. For sure. Okay, I'll try and think about it. I feel my laptop getting warmer. I think there's a... Is there some kind of thing? Kernel busy. Okay. So as long as this thing is still gray, I think.
Shouldn't have the star.
Well, this one does. Okay.
No, two less. I think the previous one was 27.
Yeah. Well, you know what I'm going to do now?
Yes. But I'm not sure if it's 24 or 23. You can start your solution and I can try that.
Yeah, I
For
know.
the next
This is
few
why I'm not
minutes.
bothering yet. So let's just, I don't know, crank it up to 200. And I
If
guess.
we set it to 1000 and we don't do this check.
No, good point.
Should we try faster?
I doubt it. Doesn't look like it.
No, I mean that internal of recalling the function we don't use it. If
well, okay.
we just
Okay. Well, then we may have an infinite loop.
How we used to return the stuff?
Well, the idea is that eventually we find the case.
And then we return CFR.
So you're comfortable with that? Okay.
Well done.
I guess we may get a division by zero error if we're lucky.
So
Okay. So let's see if we want to get
I think we should get the first number.
yeah. So the other desperate thing you can do is try and write something in Python, but no. Other than that, that's what was it that we had?
25.
20. So this is the correct. Okay, so this is the guess.
Correct. 23.
Okay.
Then we did.
So I'm going to
22 or 24.
Keyboard interrupt. What did I do? Keyboard interrupt? I did not. Oh, that was above. No, it wasn't. I did keyboard interrupt, really? Oh, this was the term. This is this. That's what that does. Okay, interesting. I guess I didn't notice that previously. Okay, so what do you want to do? You want to... Okay, so that's just...
Multiplied by 2.
And I'm not sure if we go 100,000 precision, that's probably bonkers. Anyway, okay, so I'm just going to again. So the square root of 7. No, I guess I'm maybe have it above here. No way. All right. Okay. So. we somehow have to get to the 7. So call this Q, and we say
the 7, how we get it is we multiply the bottom part with like sign plus, and then we calculate that. It's like 23 minus 16.
Okay, so I have to take the square of the number. Would you mind ripping me a page out of this?
Thank you. It's your notebook.
Huh?
No problem, it's your notebook.
I gave it to you.
Yes. Give me whole notebook and one page.
I need another one.
Is it not possible to run two things in same count?
I'm sure it is, but maybe this is easier. Need my freaking code. I think if I just see just mechanically go through an example, that I probably have an easier time getting the individual steps.
Yeah, I think I also can get the steps.
In terms of something that I can write down here, right? Because this is what we have to fill out, right?
Yeah.
And maybe I have the initial things wrong, I'm not sure. So 1 over, I guess, I have a square up here. So this doesn't have to be so precise, it just gives us the 1. And that means well, if you can tell me how you get to the 7, that would be, if you already know it, no, that would be nice.
Mm-hmm.
Just, I mean, purely based off of the 4, I guess. What else could it be?
Yeah, the SQRT and the 4, yeah.
So
you do n minus
okay.
n minus the square of d. Yeah.
So so for you the 4 is what?
D.
D. Okay, so
but this is for the first step. But for the second step, if it's not so obvious, yeah. Because the previous n is not 1. I can't think about it.
Yeah?
Yeah.
Okay. So how do I get to the 7?
Okay, so it's n. The 7 is n. What we call it n. Using that example.
Well, this is okay, let's say n sub 1.
Yeah, and it's the small n. Well, the command that we have here.
How about this here? So this is sub 1, and the n sub 1 is this what you mean? Right? This is n.
Yes.
Okay.
But also like for this, yes.
Yeah. So this is n sub 2.
Uh-huh.
Okay, so how do we get from
But it's using always like the previous n. For example, this n will use this.
yeah, sure.
Yeah.
Okay, so how do we do this?
You do the square root, not the square root, the n, the number currently you calculated.
Yeah.
Minus d square. Yeah, small d square, for example.
So this is 4.
4, yeah. 4 square over n, over the previous one.
So this is 1 minus 4. No, 1 minus 16.
No, not 1. It's the big n. It's 23. The bigger n, like the current number. The current number minus square root of d divided by the previous small n.
Okay, so then we have two different ends. Do you have it written down, I guess?
Yeah, I'm saying this big N is, for example, for 23. The current number. It will be equal to that number minus d square over the previous one, over the small n, which is the previous. We can.
But that's just the first step, isn't it? Oh, okay, wait a minute.
For example, we want to calculate the first 7.
Okay. Okay. First of all, the first thing I know is we have to calculate. So we have to calculate this approximately. First of all, this is what I think I know. So that we know what value to pull out, right? Because we know that we need to, in this case, so we start off by calculating this and pull out 4 because the first value is 4.796. And then we are left with producing the fraction for this 0.796, and for that we have to produce this this set of numbers, which is 4, 1, and minus 4.
I think the only calculation that we need is to get the 1.
Yeah.
The other is just we keep them like n, d, and as you said. So for the n, we can just do square root of not the square root, the number that we currently calculating minus d square over the last n. I can explain, for example, here for calculating, let's say we are in this step, we want to check what is the value of 2. Yes, so we do 23 minus 9, which is 14, and we divide it by this
We divide, okay, 23 divided by 7.
23 minus 9 divided by 7. So we get this. Yeah, it's the number that we currently calculating minus d squared
Okay.
over the previous n.
Okay, that makes more sense. That makes more sense.
Now we want to check for the next value of d.
Second. I don't know. I'm not sure about this. So if I do big N minus d squared over n for the second case, then I get 2 as the next. Oh. Okay. I'm just blind, that's all. Sorry. Okay, fine. Seems fine. Good. Okay, I can do this. I can do this. Okay, and then we need to get the
D.
next d.
Yeah.
And that is presumably easier.
I think for next d we should get at first L, which is we need to calculate the nth. Just
yeah, that's fine. That we can also do.
Yeah, the L is just we do the nth of that number, and then we're gonna use the L to calculate the d.
So d is okay, so we need to do this spiel up here. It's just n.
I found it. It's the current n minus the previous d. The new d is the current n minus d. And we always put minus sign.
The current n minus d.
Yeah. The current n multiplied by L minus d to be more correct.
N times L.
N times L, yeah. The current L multiplied by current n minus previous d.
Previous d.
Yeah. For example, we want to calculate here the 3.
Yeah.
And we have the previous d is 4. We do 7 multiplied by 1 minus 4, it will be equal to 3. You can take any other example. So for the second one, you can...
But wait, the first one, the n is 4.
No, the n is 1.
Right, for the first one. And the L is... Okay, and the L is also 4?
No, the L is 1.
Oh, the
current L.
Current L. Okay, so you're looking at A1, is it? Or A0?
We can look...
Let's look at A0.
A0.
Yeah.
So the current L is 1 and the current N is 7.
And what? We need to... Okay,
let's... I mean the next one.
The problem is we've mixed up, or at least one of the problems is that we're talking about, I have different notation here. For me, the L is different than what you're saying. So I'm thinking backwards.
Yeah, I think for A0 is just known.
It's just known because
it's known because it will be minus the end of the square root.
Yes, so okay, so in A0 we have L. Okay, so for me L, so this is L, right?
Okay.
So for me this is L. In the case of A0 it's 1. And you're saying that
this is A1, and for A0 L is 4.
L is 4. So this is leading. This is leading, numerator, denominator.
Okay.
I'm not sure what. Yeah. Okay. So in any case,
so for J0, like this one, it will be like special case. It will be minus the square root of the integer. But like to find out this one, how we calculated, we using this 7, like which is the n, small n.
So wait a minute. So in the special case here, D is L, I think.
Yes.
Okay. So okay. And in this case, is okay. So let's see. Is it not just simply we already have n, and so it's not just simply n minus the previous L.
Yes, but we should multiply it by it's n multiplied by L minus the previous D. Yeah.
Okay, so dp. Okay, so this is then. Okay, so we have 7 minus 4, so that's 3. and then we have 2 minus 1 is 1. Not quite. Wait, 2 minus 2 times 3 is 6. 3. Minus 3 is 3. Okay, fair enough. So what is it? 1 times 2 minus 3 minus 1. What am I missing? Okay.
For A3, it's 1 times 7 minus the previous D, which is 3. So it's 4.
Okay.
No, for A3, it should be 4.
Okay, so 3 times 2 is 6 minus...
No, we have n is equal to 7. We do 7 multiplied by 1, which is the L. L is 1 and 7 is n. So we do 7 minus the previous D, which is 3.
No, the previous D is 4. If you're looking at A2, oh sorry, oh god, I'm sorry, I missed 0, 1, 2, 3.
You are in 2.
Yeah, I was wrong. Sorry.
Yeah, for 2 we do 2 multiplied by 3 minus 3. We have n is equal. Yeah.
So 7 minus 3 is supposedly 4. Okay, fair enough.
Yeah, and then 8 minus 4, and then 7 minus 4, then 2 multiplied by 3, 6 minus 3.
Fair enough.
Yeah.
Okay, so this and this. Okay, then I guess it's more or less writing it down. You can always just try this. Nah, I'm not happy. Okay. What I'll also be interested to know is what is the longest, yeah. So let's see. L. So this is our L. Then so we need to keep it. Okay, we have AN. So what is it? First of all, we calculate D. D is simply P AN D minus L, and oh no, first we calculate N, and AN is N over N minus D AN dot D times
squared.
And then
we divide it by the
AN dot N.
Yeah.
And then we have here this is L times the calculated N, and that
L multiplied by N minus AND.
Multiplied, yes.
Yeah.
Minus AN dot D.
Multiplied.
God, sorry. Missed a shift. Okay.
And for N also we do N is nth DAN. That way. It's
what?
What is L?
Okay, so we definitely need to do integer stuff here. All I have to do is actually. Oh, okay. What the hell? Okay, if then grab a else. Okay, so let's see. I guess I can just do this. Is probably easier to read. So already off to a bad start. Actually, we should probably do it this way, so we can get the first one. So these minus 4m is 1.
For L, I'm not quite sure if that's correct.
And right. So this is.
We didn't say how we calculate L.
Isn't it just?
We do the inverse. We do the inverse of the. We do the nth of inverse of the previous number. It will be the same as the first method that we used.
Well, by previous number you mean calculating the whole thing here, right?
Mm-hmm. Yeah.
So okay, so that's an.l plus n over square root of n minus d. Maybe this is an issue with the signs. So let's see. Wait a minute.
Oh, a previous AL shouldn't be included. Should remove this. And we do another. We should remove this, and we do another of this number. And we remove the math flow. The initial value of E and D when
the initial value.
This should be int square n. And the initial value should be int of square root of n. D0. It's 4.
Okay.
Here I mean that we just we change the initial value, just the initial value.
The initial value of what?
Yeah, of the it's n of square root of n. Yeah, that one.
You mean this?
Yeah. It's same as L. Oh. I'm not sure why I'm reading it as well.
Yeah.
I was thinking.
Well, they do try. I guess the font here is unfortunate.
I was like focusing even that one.
Let me see. So there are fonts that are less stupid.
I think I am this. It's not the font.
No, but really, the font. If you have the font like this, you never mix those up.
Yeah.
Maybe I could change the font next time. Actually, maybe I can do it now. No, I won't do it. I'll do it later. Okay, so let me just. Okay, so there's a remainder, I think. There's a remainder going on here. So if you have square root of, so we're looking at the, so we're looking at some calculation. Let's see, and I think it's this whole thing. Okay, so we're looking at the calculation n divided by square root of, I think this is what we had previously. So we're looking at the calculation here. We're trying to get the rest. No, that's not quite correct, but I think, I don't know, let's call it Q. We're looking at
for the new n, we don't have to add the n.
Square root of n minus an dot d, an dot n, and then what is this? This is just the int value of that, I think. Isn't L just the int value of this?
Yes, but I said the n we don't have to add the n. Can you just do Control Z? Yeah, I was saying we don't have to add this one here. So it's
yeah, fair enough.
But it's the inverse of that.
Is it? Oh wait. Ooh, sorry. Well, first of all, I forgot to put parentheses around this.
No, it's not reference.
I guess it isn't it?
Yeah.
Okay, so let's just move that. Would have been too nice. Okay, all right, I forgot to do this. Well, let's wait till it gets it right. Well, it already didn't get it right, so okay, let's try the other obvious cases. For I in order, it's in print, boom, up, I. So let's see. Also, yeah. I should do this first. Good.
It's not correct.
Nope, it is not. So let's see. .13 is.
Oh,
this is not very good.
It's reversed.
It's reversed. 11160. There's always a 0 in there. What is that? What is that all about? So we start off with
v equal -1. Maybe we should.
Where?
Minus L. Shouldn't be.
It is minus L. But maybe it should be L.
Because we are doing minus A.
Ja. Vorzeichenfehler. Less bad.
Correct.
Is that the result?
Yeah. Yeah, we tried one. Yeah.
Okay. Okay, well, that was it. Is cool. So what?
No floating point issues.
No.
That's, I think, the point of this problem.
Yeah. Yeah. If in a lesser language, this would have we wouldn't even have been able to hack through. You would have to, I don't know. In Java, you would have decimal, big decimal, and yeah, you would have killed yourself before you got the solution.
Yeah. But yeah.
I wonder what the so we get the actual CFR. So I wonder what the large ones are. I don't know. How do we do this interestingly? So let's see. I don't even care about the mod 2 equals 0. Let's just do if CFR greater len greater 100, print I, and I guess CFR sure. So there are ones that are quite long. I guess I don't need this. I could do up to, I don't know, 10. Interesting.
2017, the longest.
Yeah.
Oh, it's close to 10,000.
Yeah. Ah, what the hell? Can I upvote without being... What is M? Oh yeah, this is just okay. So it's okay. So if it's 1 off from a square number, and if it's 2 off from a square number, or if it is a square number, is that what he's saying?
Yeah. It will produce even.
And those that have an odd divisor of the phone. Okay, fine, sure, why not? And he needed the. Why bother? For UBasic.
What is this?
I don't know, some dialect of BASIC.
Looks like past tense.
Sure.
Or pseudocode.
Well, without the types.
Yeah.
And also, I repeat until I remember what.
$800 megahertz processor.
Yes, sounds powerful.
Yeah, 1.3. I think he wrote our solution. That one is same as producing K and A. It's the same one.
This is a statement separator, I guess.
Yeah.
Not sure why he needs to count. Ah, okay. He's not even collecting them, he's just counting them. He's just counting how many. Yeah, fine. Could be.
That's the same for the last. This is our big N. We call it that the
Interesting to me is that the backslash is for division. That is
integer division, I think.
yeah. Okay. Fine.
I see he used here the iter tools to keep that following thing. Instead of having a variable, like if we see this value previously, he's collecting the total, like for example, here he will collect 1318, and if he see the same pattern, he would say,
I don't think that's really. Oh, okay.
Yeah. Repeat the process until you get a reminder which we have already seen, for which we can tell the period.
Okay, so this is where he's, yeah, you're right, he goes past it, so he remembers the position from every single combination, and if it's in there, he gets the period length, I guess.
Yeah, you want the period length, yeah.
So I'm not sure why he just did. He could just do remainders -1, I think. I mean, this is the previous pause, right? So this should already be, but okay, fine. I'm sure it's equivalent. Yeah, but it's basically this a similar insight that you can use this as a unique representation. It's just that he's doing it like this instead of having a set. Same thing here. Yes, basically the same. Cool. Also nice about this.
Huh? We used an algorithm from Wikipedia.
Cool. Oh, okay. The Arvin. Is there more deeper methods? Okay, no, this is.
What is the description on Wikipedia? Method of computing square roots. Method of computing pi. You know, there's like methods of comparing pi.
Computing
pi. Yes.
Yeah.
I remember like doing.
Is it 1/? I think there's a. Yeah, I know. It's pretty slow. But yes, it's a continued fraction. I think it's, I don't know, it's some switch around of
something related
numerator
to
and
4
denominator.
and 1/4.
Yeah, this thing.
Yeah.
Die gibt's nicht.
It's the thing is like infinite sum. So that sum, like it's it goes toward p over.
Yeah, depending on if you.
No, but it's the sum of positive integers, the positive fractions. Infinite sum of positive fractions.
No,
Okay.
No, it's different. So I think if you stop here, you're below pi over 4, and if you stop here, you're above it slightly, and so it continuously approximates it.
Yeah. But there is also sums which are sum of like a positive fraction which have infinite limit. For example, sum of 1/n squared.
Oh, this has nothing to do with pi now, you're saying?
Yeah, not sure. You can say. I think it's pi over 12. This one is pi over 12. like infinite sum of from 1 to infinity for 1 over n squared, like
Really?
yeah, like 1 yeah, 1 plus 1 over 4 plus 1 over 9 plus 1 over 16. I think it goes to it, but I'm not sure about the value. But what I'm sure about is infinite, like have exact
Limit, yeah, sure. That I believe. That I believe.
But the thing is like a sum of infinite positive numbers.
Well, you get smaller and smaller.
Yeah.
So
Mm-hmm.
is that an issue?
No. Yeah.
Okay. Yeah, I think everybody trips over that. So what do we have here? So I think this is basically, is this, okay, maybe it's not. So this is slightly different than what we have here in our problem.
No, it's
Okay. And all of the terms are in here.
oh, the initiation.
Pardon?
The initialization and everything.
Yeah. Yeah, he's just copy and pasting, this bastard.
2006.
What even is M0? Where is M0 even used? I guess it's MN. Well, anyway, I'm happy. I'm happy enough at least.